Imagine a chair that doesn't just sit there, but subtly shifts to match your posture. Or maybe a table that expands and changes its surface texture depending on, well, whether you're having dinner or
Yeah.
working.
Yeah.
What if the objects in your home weren't just static things, but dynamic, adaptive components of your environment?
It sounds pretty futuristic, doesn't it? Like something out of science fiction.
Yeah.
But the fundamental science and, the engineering making this actually possible are really happening now.
Okay.
And that's what this deep dive is all about, exploring that frontier, programmable and kinetic furniture. It's where computation meets material science to create objects that are inherently dynamic and, well, intelligent.
And we're really digging deep into the source material we have here. It's a
Yeah.
pretty comprehensive look, covering the theoretical ideas, the algorithms used to design these things, how they're simulated before they're even built, and their whole lifespan, really, right through to the end.
Exactly. Our mission today is to distill the most important insights from all this material. We want you to walk away understanding the core concepts, the technology that's powering it, and crucially, how this pretty radical shift could change the things we interact with every single day.
Right.
It's kind of your shortcut to being truly informed on a field that is redefining what physical objects can even be.
Absolutely. We're going from these sort of abstract ideas of tiny computational units inside materials all the way up to how AI is being used to design furniture that could maybe self-repair or even be reprogrammed for a completely new life when you're done with it.
Okay, so let's unpack this fundamental shift first.
Okay.
We're moving beyond, the traditional static furniture we all know, the wood, the fabric, the fixed forms.
Mhm.
We're moving towards a new class of objects that are dynamic, responsive, and possess a kind of inherent intelligence. They react to you or to their surroundings.
Right. It's a massive conceptual leap. And to really get our heads around it, there are two key terms. First, programmable matter.
Yeah.
This isn't just like a material you stick a motor onto. It's material that can fundamentally change its own physical properties, its shape, density, stiffness, maybe even color or conductivity,
Uh-huh.
based on computation happening within the material itself. It's like having microscopic compute nodes woven right into the structure.
That capability for the material to process information internally, that's what makes it truly programmable. And then you have kinetic structures.
Okay.
These are the actual forms the finisher takes, designed specifically to transform their appearance, their function, their shape through movement. It's often a fluid, complex transformation that goes way beyond simple hinges or sliders.
Yeah, I get that.
And this dynamic change can also enhance the whole aesthetic experience, changing color or texture as it moves.
This is where that hardware-software idea really starts to make sense for me. It's like the physical material itself is being coded, not just controlled by some external program.
Exactly. That moves us towards material intelligence and autonomy, where the object isn't just following commands, it's responding.
It makes the physical world behave a bit more like a digital system.
It does. And a major driver making this tangible right now is the evolution of additive manufacturing, 3D printing.
All right.
It gives us the ability to create structures with incredible geometric precision and these really complex internal degrees of freedom, which are absolutely essential for building programmable materials and kinetic forms.
You can immediately tell this isn't something one person figures out in a lab, though. It's got to be intensely interdisciplinary. Design, electronics, deep materials, science, AI, computational modeling, math. How do all these different fields actually work together on this?
Well, it's a truly collaborative process.
Mm.
Computation isn't just a tool for designers to execute a vision they already have. It's more like a partner that helps designers find solutions they might never have conceived of on their own.
Interesting.
It's a sort of co-steering process between human intuition and computational power, which is essential for navigating the sheer complexity of these systems.
So how do we even begin to model this stuff or build it? What are the fundamental building blocks, starting from the most theoretical concepts?
Okay, the theoretical foundation is really about thinking of matter not as just inert substance, but as a computationally active medium, something capable of dynamic transformation.
Like picturing matter made of tiny, intelligent particles, almost like little robots.
Precisely. The abstract idea is matter composed of these fine-grained compute nodes that interact locally. They follow simple rules, but those simple rules can produce really complex overall behavior, a bit like cellular automata.
The source material we looked at outlines different models for these theoretical particles. What are they broadly?
Well, there are models based on active agents. These are particles with computational power that can actually move and reconfigure themselves within a structure. Examples mentioned are things like amoebots or sillbots,
Okay.
and they're often focused on achieving target shapes by rearranging their positions on some kind of grid or lattice.
So these tiny things have a degree of self-awareness and mobility, at least in theory.
Yes, a degree of autonomy. Then you have models based on passive entities. These particles don't move or compute on their own.
Right.
Research here, like the abstract tile assembly model, or 8TAM, focuses on how they can self-assemble into larger structures based purely on local rules. Think of it like complementary glue strengths, making them stick together in very specific ways.
Okay, so some are like tiny robots, others are more like smart Lego bricks that snap together based on programmed rules.
You could think of it that way. And then there are hybrid models, which kind of combine the two. You have an active agent manipulating passive tiles.
Ah, okay.
So the agent has the computation and can sort of look, compute, move, lift, and place these passive components to build or rearrange a structure into a desired shape. This agent-based manipulation is really important for complex reconfigurations.
That's the fascinating microscopic theory. But how do these abstract concepts translate to, actual furniture that you can touch?
Right, that's where we move to the macro scale, bringing these ideas into tangible materials. Concepts like linkage fabrics start to emerge. This is a class of programmable materials using digital tools to define the geometry and the movement potential of interconnected physical links.
Hmm.
The source highlights that this approach allows for, and I quote, an almost infinite range of shapes, with surprisingly minimal computation, essentially just by defining the rules of connection between the links.
So you're designing the system of links, the framework, and the material itself then offers the possible forms it can take.
Exactly. And you see this translated into deployable structures, furniture specifically designed to transition smoothly between compact and expanded forms. The Delta IXI system mentioned in the material is a fantastic example of this.
Delta IEQI, okay.
It's made of 4 interconnected elements arranged in a loop, but with a diagonal crosspiece.
How does that specific geometry enable transformation? It sounds quite simple.
It's actually brilliant because the arrangement allows for deployment angles from completely flat 0 degrees to fully extended 180 degrees. Wow.
This enables a full 2D to 3D transformation and lets you vary the height and width significantly. The really key design detail is placing the pivot points at the ends of the bars, not in the center like you might expect. And using these clever non-invasive threading techniques like 1 loop or 3 loops for joints that are flexible yet stable, avoiding bulky traditional hardware.
That pivot point detail feels really significant. It changes the whole fundamental motion profile, doesn't it?
It does.
And the multi-loop threading adds stability without rigid connections. It acknowledges that geometry has always been core to furniture, obviously, but here, it's enabling dynamic, responsive transformation.
Yes, it's geometry becoming fluid and programmable. And this leads us straight to the core idea of computational abstraction of physical properties. How do you actually program a material to change its stiffness in one spot, its color in another, its overall shape?
Yeah, how do you actually tell a physical object to have, say, a gradient of stiffness, like being soft where you sit, but hard where it needs structural support? That involves numerical optimization, especially for properties like stiffness or elasticity. You work with what are called tiled microstructures, essentially designing metamaterials at the micro level
Okay.
to have very specific engineered properties. It kind of flips the traditional approach. Instead of making a material and then measuring its stiffness, it's an inverse problem. You define the desired stiffness profile first, and then an algorithm calculates the microscopic structure required to actually achieve it.
Okay, so you specify the desired behavior, like I want it this stiff here and softer there, and the computer designs the tiny internal architecture needed.
Exactly. The process described in the source material involves 2 main steps. First, a pre-computation phase where you build a library, a kind of metamaterial space of different microstructures and their known calculated properties.
Right, a database.
Then a synthesis stage where you tile the larger object with these pre-computed microstructures, making sure they connect correctly to create an object with precisely controlled, spatially varying properties.
And this is where smart materials become really crucial, right? Materials that react to outside triggers like heat or light.
Yes, absolutely. They're often integrated with 4D printing, where the material changes its form or properties over time in response to some stimulus. Heat is a common one, thermoresponsive materials. The source highlights a particularly cool example, SRW-TC wood. It stands for Programmable and Shape Color Synchronous Dual Response Wood.
Wood that changes both color and shape when you heat it. That feels genuinely mind-bending.
It really does. It's achieved by embedding thermochromic microcapsules, the things that change color with temperature, you
They're
know.
like mood rings of those old t-shirts.
Exactly. Those are embedded into dynamic covalent vitrimers. Think of these vitrimers as materials with chemical bonds that can essentially unzip and rezip when heated. This lets the material rearrange its structure, enabling shape programming.
Okay.
So one stimulus, heat, triggers two linked responses, a color change and a shape change happening pretty much in sync.
And they're even computationally designing the color changes. It's not just a uniform shift.
Yes, creating specific images or patterns that transform color when heated. This uses digital techniques like CMYK separations and laser cutting, alongside more analog methods like applying thermochromic inks.
It seems like the biggest challenge here is bridging that gap, going from those theoretical, discrete particle models to achieving smooth, continuous changes in properties and shape at a large macroscopic scale for something complex like furniture.
That is the breakthrough, moving from abstract ideas like those cellular automata models to designing actual materials like the linkage fabrics or tiled metamaterials that enable continuous complex deformations and property gradients across a real physical object.
Which loops right back to why that inverse design approach is so critical.
Absolutely fundamental. It's the shift from an exploratory process, what properties does this material happen to have, to a goal-driven one. What material structure do I need to achieve these specific properties and this specific behavior? Prescribing the desired function, maybe a specific stiffness gradient, a deformation path, a color change sequence, and then computationally designing the material structure needed to deliver it. That's the key to truly engineered programmable behavior.
And the future isn't limited to just one type of response, like heat.
Yeah.
It sounds like it's becoming multimodal.
That's definitely the direction things are heading. Kinetic designs are being envisioned that respond to multiple stimuli simultaneously, perhaps touch, sound, light, temperature, triggering coordinated changes across shape, stiffness, and color all at once.
Wow.
This requires incredibly sophisticated computational models, of course, to simulate and control that complex interacting behavior.
Okay, so we have materials that can potentially be programmed and move, and we understand sort of how to define the properties we want. How do you actually design a piece of furniture that leverages all this potential? It sounds way too complex for traditional design tools.
That's precisely why generative design, GD, is becoming so revolutionary in this field. It's an iterative process where software, guided by the goals and constraints you set, generates a huge number of potential design solutions.
Like a super fast evolutionary process.
Exactly like that. The designer's role shifts, really. It becomes less about drawing the final solution and more about defining the problem space, setting the constraints, and then curating the possibilities the software generates.
So the computer explores the vast design landscape, and the human guides it and selects the best options.
Precisely. It can explore far, far more possibilities than a human ever could manually, often discovering unexpected optimal solutions that balance conflicting requirements, things like structural integrity versus aesthetic form. It's the designer kind of co-evolving the solution with the algorithm.
What are the main algorithms doing the heavy lifting here?
Several key ones are mentioned in the material. Genetic algorithms are excellent for finding creative, efficient designs by mimicking natural selection. They iterate and select the fittest designs based on performance criteria. They're particularly useful for optimizing complex geometries.
Like evolving the ideal support structure for a chair, maybe?
Yes, exactly. Then you have generative adversarial networks, GANNs. These are powerful for creating entirely novel designs and synthetic data. In this context, they could be used to generate new material microstructures or design patterns, or even to understand the complex relationship between a microstructure and the resulting properties.
So potentially inventing materials we haven't even conceived of yet.
That's the promise, yes. Topology optimization is also fundamental. This is about distributing material within a given design space to maximize performance metrics like strength or stiffness while minimizing weight.
Right.
It's critical for designing components that will be made with additive manufacturing, helping balance multiple objectives like weight reduction and structural stability.
Making sure every bit of material is exactly where it needs to be for maximum efficiency, no more, no less.
Pretty much. And reinforcement learning, where algorithms learn optimal strategies through trial and error based on performance feedback, could potentially be used to train a dynamic furniture system. Imagine it learning how to adapt its form optimally based on user interaction or environmental cues over time.
And even the more familiar AI tools like chatbots or image generators are playing a role now.
Absolutely. AI assistants like ChatGPT or DALL-E 2 are becoming brainstorming partners for designers. They can suggest concepts, generate textures, propose color palettes that align with both aesthetic goals and functional needs. The source even mentions something called MatterGen, which sounds like an even more advanced model that can suggest entirely new material compositions based on a desired set of properties you feed it.
So AI isn't just optimizing the engineering side, it's actually helping with the subjective artistic aspects too.
It's starting to bridge that gap. While generative design arguably started in the purely quantitative realm, optimizing for stress or weight, AI tools are now assisting with more qualitative aspects, helping designers explore the full spectrum of aesthetic and functional possibilities. It's becoming a true human-computer synergy.
Because designing complex kinetic furniture sounds like a truly wicked problem, as they say in design theory.
It absolutely is. It's ill-defined, you have competing, sometimes contradictory requirements, and there's rarely a single perfect solution. Generative AI is becoming indispensable for navigating this vast, complex design space and exploring solutions that a human designer probably couldn't find manually.
And it's not just a one-way street, getting designs from the computer. It's more like a constant conversation.
That iterative feedback loop is essential. It's a continuous cycle. Human intuition guides the computational exploration, and then the computational results inform and refine the human intuition. Both the designer and the algorithms are essentially learning and evolving together throughout the process.
So you've designed your amazing programmable kinetic furniture using these powerful algorithms. How do you know it's actually going to work the way you expect it to? Building physical prototypes for every single design iteration seems, well, impossible.
That's where simulation-based validation becomes absolutely critical. Why simulate? Because as you said, physical prototyping for these complex dynamic systems is just prohibitively expensive and incredibly time-consuming.
You can't just 3D print a slightly different shape-shifting chair every afternoon to test it.
Exactly. So you create a virtual twin. This is a high-fidelity digital model that precisely predicts the furniture's behavior under a whole range of conditions before you commit to building anything physical.
Yep.
It allows for incredibly rapid iteration and really exhaustive testing, all within a virtual environment.
What are the key simulation methods being used here? What tools are in the toolbox?
Well, finite element analysis, FEA, is the core tool for structural simulation. It breaks down the complex object into a mesh of small elements, the finite elements, to calculate how stress, deformation, and stiffness are distributed under different loads.
Right, standard engineering practice for complex shapes.
It is, but the source notes it can replace a lot of physical testing with surprising accuracy, something like 5% error, which is pretty good.
That is impressive predictive power.
Yeah.
What about the special materials?
Well, for materials like composites or those tiled microstructures we talked about earlier, multi-scale modeling, MSM, is often necessary. These materials behave differently depending on the scale you're looking at, from the micro to the macro.
Oh, right.
MSM helps predict long-term behavior like material degradation over time, damage progression if it gets stressed, or even active contractions in smart materials.
So it connects what's happening at the tiny microscopic level to the overall performance and durability of the furniture.
Exactly. And crucially, for adaptive dynamic furniture, you really need multi-physics simulation. This is where you model how different physical forces interact simultaneously. Like, how does a change in temperature affect its shape while it's supporting weight and maybe responding to a touch input all at the same time? It gives you a holistic understanding of performance under combined real-world loads and in dynamic scenarios.
Because kinetic furniture isn't just dealing with gravity, right? It's dealing with movement, potentially heat, maybe electrical signals, user force, all interacting at once.
Precisely. And validating that dynamic performance is the real challenge here. It's not just predicting if it will hold weight statically. It's predicting the precise trajectories of transformation for programmable materials and designing robust adaptive control strategies for real-time responses to unpredictable stimuli. Simulating a system that is constantly reconfiguring itself requires incredibly sophisticated models.
Does simulation also help figure out if the design can actually be manufactured? Is it practical?
Yes, assessing manufacturing feasibility is increasingly integrated. Simulation tools can visualize and refine things like robotic machining paths before any material is cut or assembled.
Right.
And computational methods can also include what are called regularization terms in the optimization process. These basically penalize or prevent designs that would be impossible or extremely difficult to build with current techniques like tiny, fragile features or disconnected parts. It's a kind of design for manufacturability approach baked right into the virtual design process.
So simulation is really the essential bridge that takes you from that theoretical concept and complex algorithmic design to a virtual prototype you can trust will perform dynamically as intended and that you can actually build in the real world.
That's its vital role, absolutely. It allows for rapid iteration, helps ensure performance, safety, and manufacturability, all before you commit to expensive physical creation.
Okay, let's zoom out now and think about this furniture not just when it's brand new, but over its entire lifespan. What happens down the road?
Right. This isn't just about initial functionality. It's about adaptability, durability, and importantly, sustainability over potentially decades. The whole life cycle becomes part of the design problem itself.
And multi-objective optimization pops up again here, I assume?
It's crucial here, too. Furniture needs to balance multiple, often competing goals throughout its life: strength, weight, aesthetics, adaptability, durability, and increasingly environmental impact. Multi-objective optimization computationally finds the best compromises, what are called the Pareto fronts,
Okay.
effectively maximizing the furniture's potential utility and performance over its entire life, not just day one.
So it's a fundamental shift from optimizing for peak performance when it first comes out of the box
Right.
to optimizing for sustained performance and value across its whole existence.
Exactly. It means designing for time-dependent factors, anticipating potential degradation, and planning for long-term utility and value right from the start.
What about the idea of furniture that can repair itself? That sounds truly transformative for durability and longevity.
It is. The concept of self-repair mechanisms is directly linked back to programmable matter's ability to process information locally and respond. The source discusses theoretical modeling of these processes. Multi-scale modeling, which we mentioned for predicting degradation,
Hmm.
also helps simulate how damage might occur and how potential repair mechanisms could actually function within the material's structure.
And those dynamic covalent vitrimers you mentioned earlier are key here too.
Yes. Materials like vitrimers are highlighted specifically for their potential not just for shape programming, but also for self-healing or being reprocessed. This is due to those dynamic chemical bonds that can essentially rearrange. Imagine a scratch on your table surface just fixing itself over time, maybe with a little heat applied.
That's critical for durability and extending the useful life. And thinking about lifespan also means designing for upgradability and reconfigurability, right?
Yeah.
Making it adaptable.
Definitely. Users inherently want furniture that is adaptable and multifunctional. Computational approaches are helping design this capability in from the start, using algorithms, for instance, to explore different furniture layouts or applying principles from affordance theory to design objects that intuitively signal their possibilities for reconfiguration or interaction.
Right.
That Delta IXI system we discussed earlier is a perfect practical example, a single piece designed for significant reconfigurability and multifunctional use.
And finally, what about the very end of the furniture's life? When it's worn out or no longer needed in its current form? How does this programmable kinetic world approach sustainability?
Sustainability is paramount, and it really needs to be considered throughout the entire design process. Reducing energy use in manufacturing, minimizing waste, enabling material recovery at the end.
Yeah.
Generative design can incorporate life cycle analysis, LCA metrics, to optimize for environmental impact right from the outset. The source also points to increasing regulatory drivers, things like extended producer responsibility, EPR schemes. These are pushing manufacturers toward designs that facilitate repair, reuse, and material recovery, especially for materials like wood initially. But it's expanding. Designs with higher recyclability or recycled content might face lower fees, for example.
So policy is starting to catch up and actually incentivize circularity.
It seems so, yes. And you see parallel innovation happening in materials themselves, exploring bio-based plastics or finding ways to use waste streams like coffee grounds as raw materials. Digital tools are also aiding traditional recycling, like digital watermarks embedded in materials that high-speed sorting facilities can read for more accurate separation.
But the absolute cutting edge isn't just recycling it back into raw material, is it? The source talks about reprogramming the material itself.
That's the truly revolutionary concept enabled by programmable matter at the end of life stage. It's a significant step beyond simply breaking it down into base materials. It means computationally resetting or repurposing the material's embedded intelligence or structure for an entirely new function or form.
Wow.
It's about recovering not just the material substance, but its functional and behavioral potential. This requires developing new frameworks, maybe, to assess a material's reprogrammability index. How easily can its function be reset?
So the material doesn't necessarily lose its inherent smarts, it just gets a new set of instructions for a completely new job.
That's the ultimate vision, yes. It's a far more advanced form of circularity. Now, achieving this requires a deep synergy across several fields: advanced material science for creating these repairable and reprogrammable materials, AI and machine learning for optimizing the design and the entire life cycle management, and of course, supportive policy that actually incentivizes circularity and material recovery. Computational models will need to integrate all these technical, economic, and regulatory factors together.
Wow. This deep dive has really shown us just how radical this field is. Thinking of materials as having embedded computation, using these incredibly powerful generative AI tools to explore designs that were impossible otherwise, simulating their complex dynamic behavior with virtual twins, and then optimizing for an entire lifespan that could include self-repair and even reprogramming at the end. It's fundamentally changing what we even mean by furniture.
Yeah, the key takeaway, I think, is that we're moving towards a future where the objects around us are no longer just static things we buy and eventually discard. They are becoming dynamic, intelligent components of our living spaces, capable of adapting to our needs and being repurposed in ways we are really just beginning to imagine.
It really does make you look at the objects in your own home differently, doesn't it? Consider your own desk chair right now listening to this. What if it wasn't just a fixed shape, but could constantly adjust its support perfectly to your changing posture throughout the day, sensing how you're sitting?
Mhm.
Or what if your coffee table could not only change size for guests, but maybe subtly adjust its surface properties, becoming slightly softer for delicate items, or providing a firm, non-slip grip if you're drawing? What are the implications for how we live, how we consume, and how we interact with our physical environment when the objects themselves have this kind of embedded code and can actually evolve with us over time? It makes you wonder about the future of living products and, well, the interesting questions that arise when the things around us aren't just objects anymore, but dynamic entities.